We are in week 5 of the live session for urban utilities planning, water supply, sanitation, and drainage. The course instructor is Professor Devapratim Pandit from the Department of Architecture and Regional Planning, IIT Kharagpur. I'm Monica S. I am a research scholar at the same department, and we have a couple of streams of interaction for the course. The weekly sessions will be happening every Monday, 7 p.m. to 8 p.m. After every question or a set of questions, after I prompt, you can raise your hand, unmute, and raise your query. You can also post questions in the chat box. There is also a discussion forum where you can raise questions regarding both the weekly sessions as well as the regular course sessions. They'll be addressed either by me or by the NPTEL team, uh, either in the discussion forum or in next week's live session. So, a small recap of what we saw in week 5, which focused on water supply distribution systems and plans. So, we started with distribution systems and layout. We went on to details on the conveyance of water. We had 2 lectures on that. And sir moved on to pipes, joints, meters, and SCADA systems. And then finally to distribution network design as to how to do it overall. So for this session, we'll be primarily looking at assignment questions from the previous run of the course corresponding to week 5. First, we'll be starting with numerical questions. I'll start with one theoretical question just to give a buffer for more people to join. And then after that one theoretical question, we'll be looking at 2 important numericals, after which we'll be moving on to more theoretical questions. Depending on time availability, we'll cover as much as possible. So let's get into the session. Our first question for the day: leakage of water in the distribution system can be detected using flow meters, stress meter, hydraulic gradient line plotting, or flow analysis equipment. So which of the above are possible? Can anybody respond? Either in chat or preferably in the chat box. Okay, I think we are too early in the lecture. So let me just go on to the content supporting this question. So first of all, this is the slide from the lecture on detection of leakage in the distribution system. We can see how essentially this first option, flow meters is basically the use of some kind of water meter to detect waste. uh, if you remember from the lecture, we'll be looking at high flow of water in a period of low consumption, which means there is some kind of leakage happening. We also see hydraulic gradient line plotting, where the hydraulic line will dip in certain areas where there is a leak, where it shouldn't be dipping. And we'll also have flow analysis equipment, very similar to where you detect flow differences. However, the one option that's not there is stress meter. So, but the standard understanding of the word stress, or the layman's understanding of the word stress as pressure, doesn't really apply here. So, in conventional terms, what is a stress meter when it comes to water and water distribution systems? So, the major kind of stress meter is the crop stress meter, where we sort of measure the amount of water stress that crops are facing. Water stress is the lack of water for the plant, and you basically have a measure of either transpiration losses or evaporation losses from the plants, and the input, and therefore you determine the stress in the water, or you determine from the standard temperature and then you extrapolate from it. So there are a couple of mechanisms behind this mission. So that is a stress meter, which you are not really talking about water leakage in a system right now. And say, so what do we use for differences in pressure? We use a standard pressure gauge to detect the so-called stress in layman's terms. So don't confuse between these two. Stress meters are particularly usually used for crop stress, water stress in crops. So that's our first question. So the answer is A, C, and D. We have flow meters, hydraulic gradient line plotting, and flow analysis equipment. Let's delve into a couple of numericals. First set of numericals. For a city with a population of 10 lakh and a water consumption rate of 200 liters per capita per day, water needs to be supplied. Flow velocity of water in pipes is 1.6 meters per second. Coefficient of hydraulic capacity is 130. And the maximum.
Excuse me, can you please go to the first question for just a second?
Yeah, sure. Do you have an issue with this?
No, actually, I didn't see the options. That's why. Yeah, okay. Thank you.
Yeah, sure. So, coming back to the question. So, the details given are flow velocity of water in pipes is 1.6 meters per second, coefficient of hydraulic capacity is 130, and maximum daily demand is to be taken as 1.8 times the average daily demand. And we are supposed to be solving these two questions. So, what are the details that we have? One is population of 10 lakhs. We also have an average daily demand that is given, which is 200 LPCD, and the maximum daily demand is to be taken as 1.8 times the average daily demand, so 1.8 times the value. And then flow velocity of water, which is V, is given for us, 1.6 meters per second, and coefficient of hydraulic capacity, which is primarily used in Hazen Williams formula, if you remember, is 130, meaning it is, I mean, usually a value of 130 implies a cast iron value. So the first question asks us to calculate the diameter in meters of the supply pipes. That's so when Sir solved this, he used a standard flow rate equation, which is Q is equal to AB, if you remember. Let's look at the how to solve the problem. So these are the given values. We need to find the supply pipe diameter. We'll be primarily using this flow rate equation. Q is equal to V into A, which is discharge is equal to velocity into cross sectional area. And we'll also keep in mind that maximum descent capacity is usually measured as maximum daily demand in Qmax. Qmax is meter cube per second. So we remember from the last lectures that we usually calculate discharge in million liters per day. However, for the current purpose, we'll be calculating it in meter cube per second. So the solution is, first we look at the average daily demand of the city. So average daily demand per capita is given to us. We'll be looking at the demand for the city. This is total population into the average daily demand per capita. So the total population of the city is given as 10 lakhs, and the average daily demand per capita is given as 200. We just multiply and we get a value of 200 million liters per day. Right. So now we need to calculate the maximum daily demand for the city. So whenever you are designing a water supply network, we will be designing for this maximum daily demand and not really for the average daily demand. So in order to calculate the maximum daily demand for the city, it will be 1.8 times the average daily demand as was given in the question. So again, if you remember from the lectures, what usually what usually happens is we take 3x, 3 times the average daily demand when we are calculating the size of main lines, and for service lines we usually take a value of 2. However, this value is basically an assumption that you take. So if the value is not given in the problem, you will have to take it according to either 3 or 2, depending on which pipeline that you are deciding. However, in the current case, the problem specifies that it's going to be 1.8 times the average daily demand. So we take 1.8 to be the value. So that will be 1.8 times this average daily demand of the city, which we calculated as 200 million liters per day, which will give us a value of 360 million liters per day. So that will be our maximum daily demand. However, again, if you remember, we need to calculate the maximum design capacity in meter cube per second for us to be able to do further calculations. So we basically convert this value into meter cubes per second. So maximum design capacity, what we are calling Q here, is 360 million liters per day, right? So 360 into 10 power 6 for the million liters per. And for converting from liters to meter cube, we need to divide by 10 power 3. And this value is for an entire day's supply, right? So, and we need the unit to be per second. So we further divide by 24 into 60 into 60. So that's hours into minutes into seconds. So that will be the value. If you do the calculation, the value turns out to be 4.17 meter cubes per second. So using this value for calculating the diameter of supply pipe, this is where we will bring in the flow rate equation of Q is equal to V into A. And say we rewrite it as A, area is equal to discharge by, rather in this case, maximum descent capacity by the velocity. So the velocity value is given to be 1.6, and we just calculated Q to be 4.17, which gives us a value of 2.6 meters square. Right, but area is essentially pi d square by 4, right? So pi r square essentially. So then we calculate the value of d by rearranging this equation to get a value of 1.82 meters. So essentially, first we find out the maximum design capacity for the system, and then we go ahead and use the flow rate equation to find out the diameter of the supply pipes. So our answer for the first question under this set is 1.82 meters, right? So the next question asks us to calculate the hydraulic gradient of pipe using Hazen-Williams formula. So that is also specified for us. So this will be the Hazen-Williams formula. V is equal to 0.85 into CH into R to the power 0.63 into S into 0.54, where V is the velocity of flow through the pipe in meters per second. CH is the coefficient of hydraulic capacity, which is given to us. If you remember from the question, it's given us 130. R is something that we'll have to calculate. So R is the hydraulic mean depth of pipe in meters. Whenever we talk about the hydraulic mean depth, it's actually, you can either call it hydraulic radius or hydraulic mean depth, essentially the same. It's actually the ratio between the cross sectional area of flow normal to the flow of direction. So right now the case is for a circular pipe flowing full, but in order to explain this concept, let me just demonstrate using a half filled pipe. So say you have a sewer system. Again, pardon my drawing, I don't have proper equipment to draw, so I'm using a mouse. So say you have a pipe and then you have sewage running through. In this case, our A is the cross sectional area of flow normal to the flow of direction. So this is our cross section. If you look at the other cross section of the pipe, so I hope you can understand what kind of we are drawing this is. So if you look at the other cross section of the pipe, it's the water level is somewhere here and the water is flowing in this direction, right? Sewage is flowing in this direction. So essentially this is water, right? So when such a flow is happening, we did different color. Cross sectional area of flow normal is perpendicular to the flow direction. So our flow direction is this way, which means we'll take a cross section here, which is this cross section. If you can see, so this is the cross section. A is the cross sectional area of flow, not of the pipe but of the flow. So this area is what we'll be calculating. So how much ever is filled, and P is the wetted perimeter of the cross sectional area. So wetted perimeter is basically the part of the pipe that is wet. So it will be this part of the perimeter alone that will be taken into consideration. However, right now we have a circular pipe which is flowing full. So usually in water supply, because it is pressurized flow, the entire pipe will be full. So you have a pipe cross section and we'll have full flow. When that is the case, the calculation of hydraulic radius basically gets very simplified, and you have a value of d by 4 as the hydraulic radius, right? So right now we should be calculating the slope according to the question, and that is the formula for hydraulic radius. So let's go ahead. These are our given values, and for calculation we'll be using Hazen-Williams formula. So first we calculate the hydraulic mean depth, which is d by 4, right? We just calculated d to be 1.82 meters from the previous question, divided by 4, and that gives you a value of 0.455 meters, right? Then we use Hazen-Williams formula. We essentially just substitute the values here. So V is given as 1.6 meters per second, and then we multiply with is equal to 0.85 into 130 is the CH value, right, which is the coefficient of hydraulic capacity, and R value is given, we just found it out as 0.455 meters to the power 0.63, and we need to be finding the S value. So that's the hydraulic gradient of the. So when you solve this equation, we get an S value to be 0.0098. However, if you notice the question, it's given in percentage. So slope can be expressed as percentage. So we divide by 100 to get the value 0.098 percentage. So that's our answer for this second question of the set. Any doubts in this numerical? For
Could
those
you
of you,
please repeat the last step?
last step. So this equation,
Yeah.
you have everything plugged in except this value, right? So when you calculate S is equal to S points, S to the power 0.54 will be some value. Sorry, I'm not written the intermittent value. Say some number is coming. What you do is you take S is equal to that number to the power 1 by 0.54, which is where you get this value, right? And then,
Yeah, okay, thank you.
yeah. So if you in the question,
Yeah, I
because
got
it's
it. I
given
got
as
it.
percentage, we take a division by 100, right? Any other queries regarding this question? I hope there are no other queries, right? Let's move on to the next numerical. A water supply scheme needs to be designed for a city with a population of 15 lakhs. The average water demand is 220 liters per capita per day, and the maximum daily demand is 1.8 times the average daily demand. The pumping is to be done in two 8-hour shifts. The distance of the storage reservoir from the city is 20 kilometers, and the head loss from the source to the city is 30 meters. Determine the size of the supply mains using Darcy-Weisbach formula. We have to assume a value of f dash is equal to 0.012 and g is equal to 9.8 meters per second square. So again, this is actually, to be honest, a repeat of the employment of Darcy-Weisbach formula from the last week's class. But nonetheless, let's take a look at it. Yeah, so this is the formula that we have. HL is equal to F dash into L into V square divided by 2GD. The thing is, right now we only have from the values that are given, for example, average water demand and maximum daily demand as 1.8 times the average, and pumping is done in two 8-hour shifts. From all of these values, if you remember from the previous numerical, we can calculate the maximum design capacity, but that will correspond to Q, right? But Darcy-Weisbach formula employs V. Here we use the flow rate equation again as Q is equal to V into A in order to attain. So we substitute this. So V will be Q by A. So V square will be Q square by A square. We'll change the formula accordingly in order to get the value, right? So these are our given values. We need to find the size of the supply made, and for calculation we've been asked to use the Darcy-Weisbach formula. Similarly, as the last numerical, we'll be taking max descent capacity in Qmex, that is meter cube per second, right? So first, just like the previous question, so if you look at it, we'll be repeating the first part of the previous question. The average daily demand of the city is total population into average daily demand per capita. Total population of the city is 15 lakhs, and average water demand is given as 220 LPCD, which comes down to a value of 330 million liters per day, right? Then we calculate maximum daily demand for the city, which is given as 1.8 times the average daily demand. So we just multiply 1.8 and 330 to get the value 594, right? So that will be our maximum daily demand for the city. So the maximum design capacity, essentially converting this value into meter cubes per second. So we'll be converting this value into meter cubes per second. So 594 into million liters. So which will be 10 into to the power 6, and from liters to meter cube we divide by 10 power 3. Here when you want to convert from per day to seconds, please keep in mind that pumping is not happening throughout the day. In the previous numerical we had assumed that pumping is happening throughout the day. However, in this case pumping is only happening for 16 hours, right? Two uh, sets of 8 hours, which means in order to convert it from day to per second, we'll be dividing it by 16 into 60. So this is the number of hours, number of minutes per hour, and number of seconds per minute, right? So when you calculate the value, it turns out to be 10.31 meter cubes per second. So this will be the first part. Now we employ the Darcy-Weisbach formula. So head loss in pipe is equal to F dash into L into V square by 2GD. Again, as I said, we are going to be substituting it as uh, V is equal to Q by A. When you make this substitution here, so this part is A square, right? Q square by A square, and we already have a D, so it becomes D power 5, right? So head loss value is given to us as 30 meters is equal to F dash value is given to us 0.012 into L. L is the distance of the storage reservoir. It's given in kilometers, so we convert it to meters. So we get 20,000 meters into Q. We just calculated Q to be 10.31 to the whole power 2, and divided by 2 into G. G, the value is given as 9.8 meters per second square, and pi by 4 the whole square into D power 5. So when you solve this equation again for D, we'll get a value of D power 5 is equal to 17.41. And then when you solve this, so here we take a to the power 1 by 5. 70.41 to the power 1 by 5 will give you the value of D, which turns out to be 2.34 meters, right? So that's our answer. Any queries in this numerical? Once you know which formula to use or which equation to employ, it's going to be very easy to. You just need to figure out which values to substitute with. The trick is to know which equation to employ. So here, in these cases, the formula is given. The formula to be used is given, like Darcy-Weisbach or Hazen-Williams. No questions? All right, let's. So that's those are the two numericals we'll be dealing with today. Let's move on to some more theoretical questions. In most of the theoretical questions, I've tried to add a bit more content so that you know what's there beyond the course as well. So in this question, we've been asked to match the following and mark the option for the correct match. Right? So we have gravity system, dual system, and pumping system. Can somebody attempt to answer? Please post in the chat box.
It's C.
Right. Uh, we've got one answer. Okay, the correct
Yes,
answer
ma'am.
is yeah. Sorry, someone else said
C
something.
option, C option is right.
Okay,
According
okay. One more C. The correct option is C. Right. We have one answer in the chat box as well. So I hope everybody understands where the answer comes from. So the correct option is C, and the gravity system in this is where the reservoir is located at an altitude higher than the town where water is to be supplied. So essentially, the water supply is ensured with just gravity. Pumping system is where you have a pump and the pump directly supplies water to the tank. So throughout the day, you'll have a variable capacity pump that runs 24 hours, which is usually not a preferred system, especially because you have to keep varying the amount of water being supplied. Right. So that's one system. The dual system sort of integrates the two concepts. So you have a pump house, you pump water into an elevated reservoir, after which it's gravity that's doing the work. Right. So that's the dual system. So the answer is C. The slides, corresponding slides for the two systems are also shown here. Next question. Identify the water distribution system layout. So, is it a ring system, interlace system, dead end system, or a radial system? Any answers?
Ring system.
Yes, there's one ring system. Anybody else in the chat box? Yes, you. We have a raised hand.
Ra- ra- Radial system.
Radial system. Okay. Any other answers? Okay. So okay, we have another ring system. Right. So the answer is, if you look at the slide that was taught on the distribution system layouts, so there are two kinds of arterial loop systems. An arterial loop is when you have water incoming through loops and you have water incoming from multiple directions, possibly from multiple directions in the same point, right? So if you take this point for example, you will have water coming from here or you can have water coming from here, right? So that's essentially an arterial root system. So this one that we see is actually a ring, circular or a ring system. So people who answered ring system are correct. There is a small difference between the radial system and ring system. Both of them are arterial systems, but radial system is essentially, it looks like one reservoir located here and water supply radiating from the central point. So that's a radial system, right? So the answer here is A, ring system, right? Any queries regarding this? I hope it's clear. All right, let's go to the next question. Which statement among the given statements is incorrect? So we're looking at the incorrect statement. We have four statements given. Uh, let's look at them one by one, right? Helium A. Helium is used to detect water leakage in the distribution system. So if you remember the slides again, tracer gas, uh, essentially the use of helium is something that we use for detection of leakage in the distribution system. But just for general knowledge as to how it works, let's see how this entire system works. So there are a couple of properties of helium that make it useful in this entire venture, right? The first property is that helium is lighter than air. So what happens is when you introduce it into a system of pipes or a water supply network, and say it has a break somewhere, what happens is the helium gas molecules will exit from this crack, wherever that crack is. It will rise through the subsurface because it is lighter than air, which means it's extremely light, right? So from that crack, it will rise through the subsurface and exit from the ground at that point where the leakage is in the subsurface network, right? The other aspect is that it is an inert gas, which means it is not something that will react readily to other compounds or elements, other chemicals. So, which means it's also not toxic, it's not flammable or condensable. So, so there are two kinds of systems that we can have using helium. One is where you stop the water supply entirely and then introduce helium into the network, which means you will have drained all the water from the network and then you'll supply throughout so that you can detect where the leakage is happening, where the gaps are. However, there are some private agencies who also promise that you can use it without disrupting the water supply. Both of them have their advantages and disadvantages, but essentially, what happens in the entire operation is whether you have stopped the water supply or not. After that, you pump helium gas into the water supply line, right? And then you conduct a helium survey, which is basically using this equipment. So, this equipment will be used. It basically is a multi-gas, usually is a multi-gas detection equipment, or it could be specifically for helium as well. So then you walk through, like usually within a day people can cover from 1 to 1.5 kilometers is what they claim, like a standard survey team. So then you walk at the area where the water supply network is located below the ground. So if it is buried under the ground, you basically walk over it. And because helium is lighter and essentially it's not going to react with anything else, you will detect, and usual presence of helium in the atmosphere is very low as well, which means any detection of helium indicates that there is a leak in and around that area in the water supply network. So that's how the water leakage detection works. So essentially helium is used as a tracer gas, right? So in this, people also ensure that the entire supply network is flushed with helium, without which you might end up not detecting leaks in the towards the end of the network, right? So the second line that we have is water pipes laid in parallel induce the same head loss in each pipe. So if you remember from the uh, slides from the lectures, it is true, pipes laid in parallel will result in the same head loss in each pipe. So again, this is if you remember from school, science lab when you have water filled in a beaker and then you have water filled in a U. So you always, the level ends up being the same in both the steps, right? So say this is what it is. So essentially when you have a network and then you have two parallel connections, we cannot have a differential head loss between these two legs. So whenever pipes are laid in parallel, what will happen instead is the rate of flow or the discharge through them will vary, right? Depending on the cross section. The third statement, velocity of water in the pipe is inversely proportional to the hydraulic radius of the pipe. So we take a look at a standard formula that basically relates these two aspects. uh, Velocity of water in the pipe and hydraulic radius of the pipe. The standard equation that connects these two is Manning's formula. Excuse me. So if you look at it here, we realize that when you convert the formula from the head loss equation to the one with velocity and uh, hydraulic radius, we actually have a direct proportionality. We do not have an inverse relationship, right? So this is V velocity and R is the hydraulic radius here. Turns out that C is actually our incorrect option, right? But let's also take a look at D. Hazen-Williams formula incorporates the frictional properties of pipe material. So Hazen-Williams formula in fact takes into consideration the physical properties of the pipe and the pressure drop that's caused by friction. So different pipes offer different levels of friction towards water flow, which is where, how does the formula ensure this? By the inclusion of this CH. So CH is the coefficient of hydraulic capacity where it varies with different pipes, right? So that is how the formula takes into consideration the frictional properties of the pipe. So we realize that option C is the incorrect statement of this bunch of options. Any questions regarding this? It's basically theory, right? And I hope the helium part is also understood. Okay, any queries can be posted in the chat box later also. The next question. The circumferential stress in water pipes created by internal pressure is called as hoop stress, flexural stress, torsional stress, or bending stress. Any answers? Yeah, Mr. Rahul has posted A. Any other answers?
Frictional stress.
Sorry?
Madam. B, madam. B.
Any other answers? Okay, the answer is actually given in the slides on pressure in types of pressure in pipe. So if you remember, there are temperature based pressures, there is internal pressure, there is pressure from weight that is being loaded on to, say, the water supply network is under the ground. We have vehicles moving over and there is pressure arising out of that load. So in case of internal pressure in water creates a transverse stress or circumferential tension called hoop tension. So the answer is in fact A. So the tension is something that acts like this. So it's a circumferential tension. So there are three types of tension that arise, but the particular stress that arises along the circumference is called hoop stress, right? So it sort of acts in this direction tangentially throughout the circumference of the pipe, right? So the answer is hoop stress, right? Next question. The pipe materials that are commonly used now in water distribution lines are A. Glass reinforced plastic, B. Polyvinyl chloride, C. High density polyethylene HDPE, or D. Asbestos cement. Any answers?
B, B, C.
Sorry?
It's B, option B.
Okay, option B, which is A, B, C. You're absolutely right, actually. So, if you remember this classification of pipe-based material, based on material, sorry, uh, the blue highlights here are pipes which are used in water sector popularly right now. So, we have glass reinforced plastic. We also have PVC here. So, these are the two types of PVC that are pipes that are employed, and we also have high density polyethylene. However, asbestos cement is not something that is being used currently. There are a few major reasons for this. One is that asbestos generally has been deemed as harmful for health, and there are a couple of associations to cancer causing agents. But apart from that, the more water supply based reason is asbestos cement has a higher friction, is less smooth than the other pipes. So it's the others are preferred more than asbestos cement. So the answer is in fact B. So asbestos cement pipes are not in use for water distribution, at least uh, in the recent years. The next question. The data required for water distribution network design include population characteristics, water demand, topography, and land use characteristics. Any responses? Okay, we've got one answer in the chat box. Okay. You are right, Mr. Rahul. So, if you remember from the slides, these are the primary aspects that are required to be taken into consideration when you're designing a distribution network. I mean, even if you think of it commonsensically, it makes sense, right? So we see land use, topography, we see population and demand, right? So the answer is A, all of the above, right? So the next question. The complex loop network of water distribution can be analyzed using A. Equivalent pipe method, B. Newton-Raphson method, C. Linear theory approach, and D. Hardy-Cross method. Do we have any answers? Okay, we have one answer A. Anybody else?
D.
Okay, A, B, and D. Okay. Okay, so if you remember the equivalent pipe method is essentially when you have a network of parallel pipes, right? And you sort of replace this entire loop with an imaginary equivalent pipe. So you assume this entire loop is actually one pipe in the entire network so that calculations become easier. So if you look at it that way, equivalent pipe method is actually used for simple loop network design. So whenever the network gets much more complicated, we cannot really employ this. Imagine having 100 such loops, then we will not be able to use this equivalent pipe method to calculate the amount of flow that is happening, or the any kind of calculations that we need to do, right? Instead, we actually use these three: Hardy-Cross method, linear theory approach, and Newton-Raphson method to determine complex pipe network design. So, regarding this, all these three methods are actually um, primarily iterative methods, right? So what happens is we have essentially two unknowns. If you if you put it very simplistically, because we have too many unknowns and we don't have enough equations to sort of solve, we make an assumption saying, okay, you know what, I'm going to assume that the flow in the particular network is going to be so many, million liters per day, or so and so is the value. Then we calculate the entire network characteristics based on this one assumption. After which, there are a few parameters that we will calculate. So we cannot use any value, right? Like for network design, we want to make it as accurate as possible, or rather as close to the demand requirements as possible. What happens is, in these iterative methods, we will calculate certain parameters where the value will be say 100 or 200. Essentially, the difference in subsequent iterations for particular values should be 0 or close to 0, right? So we take an assumption, we calculate the value, and then we'll do another, we'll derive the same value from that calculation. So say we are calculating q, and we are calculating, okay, let's assume q0. So we assume the flow in the network to be q0, right? Then first iteration, we use q0 to calculate this q1. So it will be some q0 plus some difference, right? Then using this q1, we'll do the next iteration. So q2 will be is equal to q1 and some other difference. So this equation will be better than this equation. How? The value of delta will be less than the value of this delta, right? What happens is, this value, the gap between subsequent iterations of q1 and q2, the calculation of q1, will keep reducing. It will keep on going at some point at qn plus 1. The value will stop changing actually. So qn plus almost 0, say 0.001 or something like this. Then even if you keep doing the same calculation, your q value will stop changing much, and that is when you decide that that is the right value. So these are essentially iterative methods of calculation. Almost all complex pipe network designs are done using iterative methods. So Hardy-Cross method, linear theory, and Newton-Raphson, all of these are iterative methods, right? I'm not sure if you are familiar with. So, sir gave a basic idea of Hardy-Cross method, but if you want me to teach it, like I'm not prepared for today's class, but if you want to learn about it in a future class, you can always post in the discussion forum, or let me know. I can take a small session on Hardy Cross method, uh, just as a demonstration. Again, not a huge network, right? And Newton-Raphson method, if you've dealt with statistics, it's a very popular basic derivation method. So, so is linear theory of it. So all of these are essentially doing the same kind of iteration. You keep moving on to a better value of the parameter that you want to estimate, and when the value stops changing, you decide that is the value that you're trying to estimate, right? So the answer for this complex loop network of water distribution can be analyzed using B, C, and D. So equivalent pipe method is something that we use only for simple loops, right? Let's look at one more question. Dash are used to determine the volumetric flow of water directly from its velocity. So these are essentially water meters, right? Types of water meters. So A, rotary piston meters; B, electromagnetic meters; C, ultrasonic meters; and D, inferential meters. Any answers?
Ultrasonic.
Okay, we have one answer, ultrasonic. Anybody else? The inferential meters. In this case, Mr. Ashwin is right. The answer is inferential meter. So, if you look at the rotary piston meters, is something that uses measures the flow of water directly, as in it the calculation directly corresponds to the volume of water, right? Inferential meters actually use the velocity of water, so they measure the velocity of water and then they figure out the amount of water being used, right? Electromagnetic meters actually use differences in voltage, and ultrasonic water meters essentially use sound waves and they measure the difference in time. It's not velocity, right? So essentially the amount of the speed changes when they're moving against the water flow, and that's how they calculate uh, the flow of water, right? So the answer is actually inferential meters, D, right? So I think we have one more question. So dash has the least coefficient of thermal expansion. UPVC pipes, concrete pipes, cast iron pipes, and HDPE pipes. Any answers? HDPE pipes. Okay. Any other answers?
B. Concrete pipes.
Yes. So you are right, ma'am. And we have another answer in the chat also, is it right? So the answer is concrete pipes. So if you remember, that's actually one of the advantages of concrete pipes, that it has the least coefficient of thermal expansion. So look at it logically. Metal basically expands readily when it comes to when it's exposed to heat, and pipe essentially starts like high heats, and PVC pipes start melting, right? So concrete pipes have a very low coefficient of thermal expansion. So that's the answer. I think this is the last question. Chessy's formula for open channel flow does not consider hydraulic mean depth, slope of the pipe, length of the pipe, and area of flow. Any answers? Excuse me. Okay, so the answer is actually length of the pipe. So we have these parameters. When you remember, if you remember the Chessy's formula, we use A, which is area of flow water, M is the hydraulic mean depth, and I is the slope of the bed, C is a constant, right? So people might always bring up this issue that, well, don't you actually take length into consideration when you're using slope? The thing is, no, not actually. So slope is a particular property. We might use the length of the pipe to determine, or the distance between two points to determine the slope, but nonetheless, the slope does not actually require the full length to be calculated, right? You can just determine the gradient. If you measure at any 2 points, you can determine the slope. So the answer is C, length of the pipe, right? So that's all for this week. I hope presentation was useful.